Hey everyone. So in the past 1.5 years, I've gotten to teach multiple courses in machine learning as part of the professional master's program at University of Washington, Seattle. What I've noticed is that students come with a good understanding of, let's say, deep learning or natural language processing, but may not be comfortable talking about overfitting or regularization, some of the classical and fundamental machine learning concepts. So this bite-sized video is to address that gap. We'll go through a demo on TensorFlow Playground, where we'll illustrate these concepts. And before that, we'll cover some of these concepts in theory. If you're already comfortable with these concepts and you want to skip to the demo, feel free to go ahead. Otherwise, we can go through the concepts now and then get to the demo. Okay, so one of the first and most fundamental concept in machine learning is the concept of linear model, where if you are looking at a classification problem, a linear classifier, for example, as an instance of linear model, can separate the two classes. You also have linear regression. So linear model is simple. You have a linear function, let's say f of w is w transpose x, that's good enough to discriminate between two classes or fit, in the case of regression, fit through the points. And because it's linear, it is simple, but it has its limitations. You cannot do really complex discrimination. So that's where we have nonlinear models. So here's an example where your two classes, the positive and negative labels, are set up in a way that no linear model can actually discriminate the positives from negatives perfectly. So this is also called the XOR function. You can see it's exclusive OR. So if x-axis is 0, then the y-axis, or if x1 is 0, then x2 is 1. And if x1 is 1, then x2 is 0. So this is the XOR, right? So there is no linear model that can fit an XOR. So only nonlinear models work here, right? So this is an example where you need a nonlinear model. And a lot of real world business problems that we face require nonlinearity. And this is something that deep learning, for instance, can help with quite a bit. So we'll get to deep learning in a bit. One fix that people used to do earlier a lot, which falls in the category of feature engineering, is to use linear models, but with nonlinear features. Consider, for instance, you have two raw features, x1 and x2. And x1 is a linear feature, x2 is a linear feature. x1 squared is nonlinear, x2 squared is nonlinear. So now a linear model with nonlinear features would be w1x1 plus w2x2, though that's the linear part. But then w3x1 squared and w4x2 squared. So x1 squared and x2 squared are nonlinear features, but the model itself is linear because it's linear in w. So this is a hack where you can still have a linear model, but use nonlinear features and get something that has a nonlinear decision boundary. So for instance, here, when we use x1 squared and x2 squared, if w3 and w4 is equal to 1 or they're equal to each other, then you form a circle, and anything below that circle, you can say it's a negative class, and anything above the circle is a positive class. So for instance, this x1 squared plus x2 squared as an alpha is represented by the area within this dotted circle. So using nonlinear features, you can learn nonlinear decision boundaries such as a circle through a linear model. So that's a hack where you can use nonlinear features. So in earlier days, people used to invest a lot in feature engineering and constructing good nonlinear features. But with the advent of deep learning, you don't have to do it anymore, right? So deep learning is doing feature engineering for you in an automated way, in a data-driven way. So you don't have to invest time doing feature engineering yourself. So one of the simplest and the most powerful general purpose nonlinear models in machine learning or deep learning is the feed-forward neural network. So this is something that still gets used in the industry. It's not all transformers. It's not all CNNs. You're looking at natural language or vision, then transformers and CNNs apply. But a lot of real world business problems still require the use of feed-forward neural networks. Even transformers, if you're using transformers, for your downstream task, if you're doing sentiment analysis, you might still use a feed-forward neural network for fine-tuning. So fine-tuning still uses feed-forward neural networks, right? So let's look at this feed-forward neural network. Here we have the raw features, I've kind of discriminated here between linear and nonlinear features. So x1 and x2 is linear, x1 squared, x2 squared is nonlinear. You may or may not choose to use nonlinear features in your model, right? Because you may not have access to the good nonlinear features. So let's say you have linear features and maybe you have nonlinear features. Then we have the hidden layers, so which are in red. The circles in red represent the hidden layers. So here we have 3 hidden layers, H1, H2, H3. And you have the output layer, which is typically softmax across your classes. So here, let's say you have 2 classes. So you have 2 nodes that represent the positive or the negative node, and then you get a probability for each of them. And based on that, you can do the classification. We also have activation functions, F1, F2, F3. And so these could be ReLU, GeLU, TANH. They could be sigmoid. Sigmoid typically don't use it in hidden layers. Use it in the final layer. And the hidden layers here have 4 neurons per layer. So there's 3 hidden layers with 4 neurons per layer. So this is just an example, right? So here, if you look at hyperparameters, you'd say, well, my hyperparameters have the number of hidden layers, the number of neurons per layer, and the nonlinear activation function I'm using in the hidden layers, okay? And these are some things that you'd have to tune, right? You'd have to tune for the hyperparameters if you are in the scenario of overfitting or underfitting. So let's look at overfitting and underfitting. Another important fundamental concept in machine learning is as you are training, your train error keeps going down, especially if you're overfitting, you can actually get a 0 training error. It's quite possible if you're overfitting that you have a 0 training error. But what happens to the validation and test when you overfit is the test error and the validation error starts to go up. And that's when you know you're overfitting. So this dotted blue line here is the boundary of where you say you're starting to overfit. And below this, or to the left of this, you're underfitting. So you're not fit your data well enough to make good predictions. But if you go beyond the dotted line, you're overfitting. So you're not really, you're fitting to the training data, but you're not generalizing to the test or validation data set. So right around where the dotted line is where you would say is a point of good fit, right? So concepts of overfitting and underfitting, right? So let's explore all of these concepts. So maybe you're already familiar with these concepts, right? Or maybe it's a refresher for you, but let's actually dive into this cool demo on TensorFlow Playground. So we have, if you're looking at this in on LinkedIn, then you can check out the YouTube video, which is basically this video. So we'll go into the TensorFlow Playground demo right away. All right, so we have the TensorFlow Playground. This is something you can explore on your own, but I find it very illustrative, very helpful to understand all the concepts that we discussed, the fundamental concepts that we discussed so far. So playground.tensorflow.org is the link where you can look up this demo. So let's play with the data sets that we have available here. So on the left, you see there are 4 data sets, the circle, the XOR, the spiral, and just a regular data set that a linear model can fit with. And on the top, you see epochs, which is the number of passes through the data, learning rate, which is important. There's also a hyperparameter. Too high a learning rate, you may either be going very fast, converging very fast, or not converge at all. Too slow, low learning rate, you're probably not converging, going too slow. Activation functions, we have ReLU, TANH, sigmoid, linear. Sigmoid is typically used only in the output layer, whereas TANH and ReLU gets used in the input layers. Linear is rarely used, but for instance, if you're having a CNN, like a model for vision, and you're going from the CNN to the feed forward, that's where you might want to have a linear layer. So there are places where linear layers still make sense. Regularization, L1, L2, useful when you're overfitting and you have rates for those. We'll look at classification. So this is the setup. Right now we have 0 hidden layers. So we just have the input x1, x2, and they go right into the output layer using a sigmoid activation function. Okay. So if I were to run this, it discriminates really well. You can see the white line here discriminates the orange from the blue, and you see the training and test loss is 0. So it's a perfect fit. And we can discriminate really well. So, okay, great. So we don't need any fancy model for this data because the models are well separated. It's linearly separable. So nothing much to do here. Let's go to the next use case. Let's try this. So the circles, 2 circles. Um, Here, I want to show you, okay, let's try the linear model. So let's try a linear model. Uh, doesn't really do much. You see the training loss and test loss are pretty high, and it's not really doing discrimination. So it's saying it's dividing it vertically, and so it's not a good fit. It's not classifying the orange. It's not separating the orange points from the blue points. It's not drawing a circle, which is the ideal uh, decision boundary for this data set. Okay, let's do something. Let me reset this. Let's add nonlinear features. So x1 square and x2 square. Okay, so we know that x1 squared plus x2 squared forms a circle. So if I have 0 hidden layers, so that means it's a linear model. If I run this again, great, I'm able to discriminate the blue from the orange because I'm using a nonlinear feature. This is still a linear model like we discussed in the video earlier, but it uses nonlinear features and hence you can discriminate really well. Okay, great. Let's assume we don't want to use nonlinear features. Let's say we didn't know x1 squared and x2 squared is good. How would we actually uh, build a nonlinear model? So we need to add some layers here. So let's add a couple of layers. Let's try this and see if I have a tanh activation function. Does it do a good job? It's kind of doing an okay job. I'm at 500 epochs already and not, yeah. So it's actually struggling to discriminate the blues from the orange. Okay. So I'm already at 1000 epochs. I'm going to stop. Let me change the activation function. I mean, let's just see if it changes anything. You see, ReLU activation function is a rectified linear unit. It likes linearity. So you see this linear surface, right? Because it likes, it's a combination of linear functions. So with a cutoff. So ReLU is giving me more of a kind of edge-based decision boundary, whereas tanh was giving me more smoother decision boundary. Okay, but even ReLU is not able to discriminate. We're already at 1000 epochs. So let's add a few more layers. Maybe that'll help. Let me add a couple of more neurons as well. So 4 neurons in each layer. Okay, let's try ReLU. Okay, great. So you see right away, we are only at 100 epochs. Adding more layers, increasing the complexity of the model, making it more nonlinear, I can now discriminate. It's actually fit a 1, 2, 3, 4, 5, 6 hexagon. So hexagon is the decision boundary for this data. If I change it to tanh, I just want to see if tanh is also good enough. Okay, tanh also did it in about the same number of epochs. So, but it got me a circular decision boundary instead of a hexagon. But both of them are discriminating the orange points from the blue points. So great job. And actually, we had a regularization here. So let's see if I can remove the regularization. Let's see what happens. Okay, I still do a good job. Great. Okay, so without using any nonlinear features, just using the raw features, adding 4 hidden layers. So 4 hidden layers was required for me to discriminate the orange points from the blue points. 2 hidden layers was not sufficient. So this is the role of hyperparameters here. So we needed a sufficiently complex model. You can see the training loss and test loss are close to 0. So we're not overfitting, but we have a complex enough model that we can discriminate. Okay, so we covered 2 data sets. Let's move on to the third data set. So this is the XOR. You can see the orange points form the XOR and the blue points are the negation of XOR. So we already have 4 hidden layers here. So let's try it out. Let's go for it. Okay, great. So with 4 hidden layers, I'm able to discriminate the blues from the greens. And if I change the activation function to ReLU, it's taking a little bit more time, but it got there in 200 epochs. Now let's change it to sigmoid. We'll see why sigmoid is not so good. Okay. Yeah. So you look at the train and test loss here. It's 0.5. It's kind of flattened out. It's not making progress. So a bad activation function. Sigmoid is a bad activation function for hidden layers, right? So we're going to switch back to ReLU. What if I decrease the number of hidden layers here? It still does a good job. Okay, let's reduce it even further. Just 1 hidden layer. Still does a good job. Okay, 0 hidden layers. Sorry, can't do that. So with XOR, just 1 hidden layer, and I am able to discriminate. So that's it's still taking time. So there's some randomness also involved because depending on your starting point, you might converge sooner or faster, right? So this is XOR is ReLU struggling here, but let's try. tanh is also struggling. Okay. Wonder if the starting point had something to do with this. Interesting. Let's add a few neurons. Okay, yeah, we needed 4 neurons. Okay, that's probably why. Okay, right. So if I have 4 neurons, I can actually discriminate. If I had only 2 neurons, I'm not able to do that. Okay, so with 2 neurons, so it's not just the number of hidden layers, it's also the number of neurons per layer. As you can see, that helps me discriminate. So going from 2 to 4 neurons, and I'm able to discriminate between the two classes. Okay, great. So let's look at the last data set. This is the most complicated because you can see the orange data points are interleaved with the blue data points in a spiral fashion. So it's going to be hard for these models to discriminate, but let's just try. Okay, let's try TANH. You can see the test loss is 0.5, training loss is 0.445. There's a gap, not a huge gap, but there's no progress. There's no progress being made. We're already at 600 epochs. And it's doing a bad job at discrimination. And you can see that because the test loss and training loss are high. So that's the amount of error you have with this model. So not doing a great job. Let's add a couple of more hidden layers. Let's see, maybe with 3 hidden layers, can we get it to work? You can see the test and train loss are diverging. So now we are overfitting, right? That's where test loss is diverging from the training loss. Yeah, so this is really, really overfitting. You see, it's really complicated. It's not even getting me a spiral. It's doing something really weird. And there is overfitting. As you can see, the test loss is different from the training loss. Okay, we're already at 1,000 epochs. We stop. Let's add a couple more hidden layers. And try again. Okay, so it's really struggling. So you can see the test and the train loss, there's a lot of gaps. And also the function is not really smooth. It's actually going in the zigzag manner. Maybe regularization will help. Let's try L2 regularization. 0.001 is the regularization rate. Let's try that. 100 epochs. There's some struggle going on. Okay, this is an interesting phenomenon too. You see the functions already converge. It seems to have converged, but if you go beyond a certain number of epochs, it can actually go down. So we saw that in the last run. Okay, let's try ReLU. I've explored TANH, but let's try ReLU and see if it actually helps. ReLU is making progress. 500 epochs kind of converged. Okay. All right. Okay, so it's kind of converged, but it's not doing this crazy zigzag thing. Let's add a few more neurons here. 6 neurons per layer, 5 hidden layers. Let's try that. So using a more complex model, but I also have regularization to take care of overfitting here. You see the loss is going down rapidly, and it's actually getting the spiral shape. It's doing a good job. The test loss and the train loss is good. So this is fitting to the data, but it's not overfitting as per the test loss, right? So it got the spiral shape down, but it might be overfitting. If you were to extend the spiral, you see it's kind of fitting the spiral right now, but if you were to extend the spiral, maybe it'll actually get it wrong. So then you need more data. So okay, so ReLU got this right. Let's try TANH. Okay, TANH is starting to converge as well. 500 epochs, and it's struggling. Yeah, so we're hitting 1,000 epochs and not yet gotten the spiral down. Okay, so this tells us that ReLU is a better activation function than TANH, at least for this data set. So this is how through hyperparameter tuning and exploration and running a lot of experiments, you figure out combinations that work well. So hope you like this video. We looked at different concepts of overfitting, regularization, linear models, nonlinear models, linear models with nonlinear features, and train, test, error, and we explored all of many of these concepts through this demo. Thank you so much. We'll catch you in another video. Yeah.